In this video, we'll see another procedure for addressing the overfitting issues in deep neural networks known as dropout training. So we saw previously that if we're having overfitting issues in deep neural networks, we could use unsupervised pre-training. And now we'll look at the other procedure for fighting overfitting known as stochastic dropout training. So to avoid overfitting, again, the idea is going to be that instead of directly optimizing what we would normally optimize with backprop, our training loss, we'll try to somehow divert the training procedure so that it does something else. So for unsupervised pre-training, we had it do some unsupervised learning as an initialization phase. And for dropout, we're in a sense going to cripple the neural network while it's training by removing stochastically hidden units. So in the basic version of Dropout, what we do is that for each hidden unit, once we've computed it, we also independently will set it to 0, so essentially throw away the actual value the hidden unit had by, say, multiplying it by 0, sending it to 0, with a probability of 0.5. So for instance, if we had this neural network, and imagine that we computed the first hidden layer. Then once we do that, we actually, for each hidden unit, will set it to 0 with a probability of 0.5. And we're going to sample this possibility of setting it to 0 independently for each hidden unit. And then, so then some hidden units will be set to 0. And then we repeat this procedure for computing the second hidden layer. We compute all hidden units, and then again, stochastically, we'll set some of them actually to 0 instead, and we continue this until we reach the output layer where we don't apply this sort of masking noise. And so, for instance, one result of this sampling procedure could be that we would be setting this one to 0 at the first layer and this one to 0 at the second layer, which means really that we would be computing this a subset of hidden units at the end, and the connections that are really used during forward propagation would correspond to those that do not go into or out of the masked or dropped out hidden units. As you can see, this is similar to the type of noise we would add in denoising autoencoders. One difference is here that we're doing this at the hidden unit level instead at the input unit level. And the other difference is that we're not training an autoencoder here. So when we're doing this, we're actually doing it while we're doing backpropagation in supervised learning with a neural network. So the impact of this is that now the hidden units cannot assume that all hidden units in the same hidden layer are going to be present. And so they cannot co-adapt to these other units. They cannot sort of collaborate to generate these complicated patterns that might be useful for fitting the training data, because now they cannot expect that all hidden units in the same hidden layer are going to be present. And so by breaking this co-adaptation behavior that the hidden units could have, the idea is that now each hidden unit will be forced to sort of focus on extracting a feature which is useful in general, and not just when used in combination with all hidden units. They still need to somehow do things that are different. So there's not no sort of collaboration between the hidden units, but they cannot develop as complicated co-adaptation patterns between themselves because they cannot assume that all other hidden units are going to be present there. Some of the other hidden units will be set to 0 stochastically. And in the basic version, we use 0.5 as the probability of setting to 0. We could use another probability. This could be a hyperparameter. But in practice, it seems like 0.5 works really well. So how does that change the regular forward and backward propagation algorithm for training a neural network? Well, let's assume that for each hidden layer, we've sampled these binary masks. So we could do this before doing forward propagation, and I'll call these binary masks MK, where K is an index for the hidden layer. We'll compute our pre-activation like we do normally, but now what we'll do is that we'll change the definition of the hidden layer by incorporating this multiplication with a 0 if with probability 0.5 we decided to set the hidden unit to 0, and otherwise by multiplying by 1 it means we retain the value of the hidden layer. So this idea of dropping out hidden units, we can just implement it by multiplying by this binary vector that we sample every time we do forward propagation. And that's actually important. If we put the same training input here at two different forward propagation steps, we will sample different masks, or at least we'll sample individual masks, which will almost certainly be different. Okay, so that's very important. The mask always changes and is sampled stochastically. And that's really the only thing that changes in the algorithm. Before, when we compute the hidden layer value of a hidden unit, now we compute the activation vector and then we multiply it by this binary random mask. And when it comes to doing backpropagation, again, the only thing that's going to change, actually there are two things that are going to change. The first one is that because in the definition of hk minus 1 or hk, we were taking the activation, what used to be the activation vector, and multiplying it by a mask, then when we're backpropagating the gradient up to the pre-activation, we also need to multiply by the chain, because of the chain rule, by the mask vector. And so this means that at this level, many of the gradients will be actually set to 0. So there won't be a backpropagation that flows through. So no gradient will go through a hidden unit that has been dropped out. So this will be the consequence of this, and we can derive this just by the regular chain rule for in the context of a neural network. So that's the first thing that changes. And the other thing, which doesn't really change but we should take into account, is that this vector now incorporates the mask. So this is the masked activation pattern. And so we should not forget that here this is not the this is a vector that contains a lot of 0. On average, 50% of its entries are going to be 0 because it's what used to be the activation vector multiplied by the mask. Okay, but that's all that changes. Otherwise, the regular backpropagation algorithm remains essentially the same. It's just the incorporation of these masks that drops out hidden units. So that's for training. When we're training, we have to sample these masks for every training example and slightly adapt the forward and backward equations. But at test time, instead of getting something that's stochastic, what we will do is that we will replace the masks by their expectation. And so for instance, if we sample with probability 0.5, we will actually set the hidden unit to 0 and drop it out. Then the mask at test time would be a vector filled with the value 0.5. So that's the expectation of that binary vector. So actually in the single hidden layer case, we can show that this is equivalent to taking a decision at test time which is based on the geometric average of all neural networks, single hidden layer neural networks, with all these possible binary masks. So it's as if we're building this ensemble of an exponential number of neural networks that we're combining together through a geometric average. So just as a reminder, if we have a number A and a number B, if we're taking the geometric average, it would just be the square root of the product. And just in general, if you have, say, 3 numbers, then it would be the product to the 1 over 3. So that's the geometric average. And so we can think of it as an average in the log space. So if I took the log of this, it would just be 1 over 3 of the sum of the log of these values. And then we take the exponential back, and that gives us our geometric average. And so intuitively, in machine learning, we know that the best systems that rely on machine learning, or if we want to improve the quality of a system, one fairly reliable way of doing that is to construct an ensemble of many trained models. Well, we can think of dropout training as doing this in a very efficient way. We don't actually have to train an exponential number of models. We just get them as a byproduct of the training procedure at test time by just taking replacing the mask by this 0.5 probable, this vector of value with the value of 0.5 in every entry. That's only true in the single hidden layer case. For multiple hidden layer, this story doesn't really follow through, but we still see in that we get much better generalization with this. We could combine this with unsupervised pre-training. So we could do unsupervised pre-training, and then instead of using regular backprop, we would use dropout backpropagation. And in general, this procedure, either with unsupervised pre-training or also alone, allows us to get very, very good results in many data sets. I won't go over them, but you should consult this paper by Jeff Hinton and colleagues that provide a lot of evidence that this is a very good, better way of training training a neural network to get good generalization. And I would also add that one disadvantage of Dropout is that training can be slower, but it has if you're willing to put more computational time in training, then what we find is that often it will indeed yield with much better results at test time. All right, so that's it for Dropout training.